All right, today we're going to talk about power, and we're also going to briefly show how to use energy diagrams. So power is the rate of work being done, or the work per unit time. So power is d work over dt, how much work is being done per unit time. The units are watts, right? dW has units of joules, dt has units of seconds. 1 joule per second is what we call a watt, which is also, of course, a joule is a Newton meter, so a watt is a Newton meter per second, or kilogram meter squared per seconds cubed. Now, remember that work is the integral of force dot distance. That means that if I make a little tiny step, if an object moves a tiny distance dx, the little bit of work that's done on the object dw is just force dotted into that little displacement dx. Well, power is d work dt, but a little step in work is just force dot dx, but dx over dt is velocity, so we can also think of power as force times velocity, or we can calculate power. The rate at which work is being done is just force dotted into velocity. Another way you can come up with that same relationship is you can say, well, look, power is the derivative of work with respect to time. But I do a little bit of work that causes a little change in kinetic energy. So power can also be thought of as change in kinetic energy per unit time. But the derivative of kinetic energy with respect to time is just the derivative of 1/2 mv squared with respect to time. When I take the derivative of that expression with respect to time, 1/2 and m do not depend on time. V does. So I can use the chain rule, and the chain rule says that the derivative of v squared with respect to time is the derivative of v squared with respect to v times the derivative of v with respect to time. And the derivative of v squared with respect to v, of course, is just 2v. So I do that derivative, and I just get mv dv dt. But of course, dv dt, the change in velocity with respect to time, is just acceleration. So power is the derivative of kinetic energy with respect to time, and that's just equal to mv times acceleration. But mass times acceleration is just force, so that means that power is force times velocity. All right, in this case, we lost the dot product because we were assuming a one-dimensional problem. But anyway, that is a useful thing to remember, that power is the rate of work being done per unit time, but it can be found by just taking force times velocity. And here's an example that uses that. An automobile is driving down the freeway at 80 miles per hour, 35.76 meters per second. Air drag creates a force on the car with a magnitude of 432 newtons. What power does the engine need to produce in horsepower to overcome air drag? And 1 horsepower, it turns out, is 745.7 watts. So how do we work this problem? Well, the power that the engine needs to produce is the same as the power created, caused by, that slows the car down with respect to air drag. So power is force times velocity. Sorry, there should be no d here. Just force times velocity. And of course, we know the force due to air drag is 432 newtons. The velocity is 35.76 meters per second. So the power, the rate at which energy is lost to the car, which is equal to the rate at which the engine needs to produce energy, is about 15,000 Newton meters per second, or a Newton meter is a joule, so about 15,000 joules per second, and a joule per second is a watt. Okay, so about 15,000 watts. Now we need to convert that to horsepower, so we multiply by 1 horsepower over 745.7 watts, and that gives us 20.7 horsepower. Now, typical automobiles have engines that can produce anywhere from on the order of 100 up to maybe 1,000 horsepower, right? So, your basic end ultra small car would have something of the order of 100 horsepower, and a big truck that was designed to haul loads would have something closer to 1,000 horsepower. So 20 horsepower is a small number, right? So this drag is something kind of typical of what you'd get for a mid-sized car. And so a mid-sized car has more than enough horsepower to overcome this drag. So why do they need engines with so much horsepower? Well, they need to accelerate, right? They need to not just maintain their velocity, they need to be able to speed up. So let's work this problem. A 2000 Ferrari 360 Moderna can accelerate from 0 to 60 miles per hour, 26.82 meters per second, in 3.7 seconds. If we ignore losses due to friction, drag, etc., what average power must the engine produce to achieve this? Give your answer both in watts and horsepower. The mass of the car is 1390 kilograms. All right, so the way we work this is we say, well, look, power is work per unit time. So the average power is just the total work done in the total time, or the total change in kinetic energy per unit time. Well, we're starting at zero velocity, and change in kinetic energy is just K final minus K initial. So K initial is zero. That means in this case, the average power is just the final kinetic energy divided by the time. And of course, kinetic energy is 1/2 mv squared. So we can plug this in, and actually, I wrote the question and said give the power in watts and in horsepower, but I'm only going to give it to you in horsepower. It turns out it's 181 horsepower. That's a lot larger than the 20 we got before, but it's still a lot smaller than the horsepower that the engine in a 2000 Ferrari would be able to produce. This particular car has a 400 horsepower engine. So why can't it accelerate faster? Why can't it get up to 60 miles per hour faster if the average power to do that is 181 horsepower, but the engine has 400 horsepower? Well, there's a limit on how much of your engine's power you can use because you can't have your wheels slipping. So let's consider the static friction that you need in the wheels in order to accelerate you. So if a 2000 Ferrari 360 Moderna accelerates with a constant power of 181 horsepower from 0 to 60 miles per hour, what minimum coefficient of static friction do the tires need to have? The mass of the car is 1390 kilograms. So once again, power is force times velocity. And so in order to accelerate the car with that much power, it needs to be able to generate that force in the wheels. But in order for the wheels to accelerate the car without slipping, that force has to be the static friction force. And of course, static friction is the static friction coefficient times the normal force, which is mg, and then we multiply that force by velocity to get power. So we know how much power we're generating, and we know the mass of the car, we know g, we know the velocity, we can find the required static friction coefficient. All right, so we plug in the 181 horsepower, and we plug in the mass g, and we plug in the maximum velocity, and we find that the coefficient of friction is 0.369, and in the top we have watts, which is joules per second, which is Newton meters per second, and at the bottom we have kilogram meters per second, which is newtons, times meters per second. So all the units cancel out as they should, and we just get our coefficient of static friction of 0.369. Now, car tires typically have coefficients of friction much larger than this, 7 or 0.7, 0.8. So why can't the car accelerate faster? It looks like we're only using 0.369 as our static coefficient, right? So our tires should be able to do more. Well, remember, the velocity plugged in here is the final velocity, 60 miles per hour. So that is the coefficient of friction we would need in order to accelerate this car with 181 horsepower without the wheels slipping at 60 miles per hour. But when we're accelerating, we're not always at 60 miles per hour. We start out at zero. What happens if you plug zero velocity into this? You get infinity. All right, so initially you cannot use much power because the tires will just slip, you'll peel out. So to get your maximum acceleration, you have to start with lower power, and as the velocity gets bigger, you can increase the power that you're using. And so probably by the time it gets to 60 miles an hour, it's probably using most of that horsepower, most of that 400. But earlier on, you're using much less power, and so it averages to something significantly less than 400 horsepower. All right, now let's quickly talk about energy diagrams. The idea with an energy diagram is you just make a diagram, you make a plot of energy as a function of some variable. For gravity, we're going to plot energy as a function of y. This black line here is the total energy. So if I throw a ball up and it comes back down, all right, the total energy is constant, all right? There's kinetic energy. As the ball goes up, the ball slows down and I lose kinetic energy, but I gain potential energy. So the potential energy due to gravity is shown in blue. At y equals 0, there's no potential energy. And then as y increases, the potential energy increases linearly. So where's the kinetic energy in this plot? The kinetic energy is just the difference between the total energy and the gravitational energy. So the potential energy plus the kinetic energy equals the total energy. So as my ball goes up, it loses kinetic energy as it gains gravitational potential energy, such that the total energy of the ball remains constant. Right here where the blue and the black lines cross, that's the maximum height of the ball, because once it gets up there, it has zero kinetic energy. All of the energy is potential energy. If it were to go higher, it would have to have negative kinetic energy, and you can't have negative kinetic energy, not in classical physics anyway. So that tells us when it gets to that height, all of its kinetic energy has been turned into potential energy, and then it comes back down. And as it comes down, it loses gravitational potential energy, but it increases in kinetic energy, once again, to keep the total energy constant. And here is an energy diagram for a spring. Right? If I put a mass on a spring and I compress it, all right, the black line, once again, is the total energy. And the blue line is the potential energy of the spring. Now remember, the potential energy for a spring is 1/2 kx squared. So when the spring is at its relaxed length, there's no potential energy. But then as we stretch the spring or compress the spring, its energy goes up. All right? And the kinetic energy is just the difference between the total energy and the spring potential energy. So these points here and here, where the black and blue lines cross, that's where the kinetic energy is 0. So those are the turning points. We won't go past that. So if I have a mass moving with some kinetic energy on my spring, as it, if let's say it's at x equals 0 with a certain amount of kinetic energy, these points up here, that's when it runs out of kinetic energy. All the kinetic energy has been converted to potential energy, and that's when the mass stops and turns around and comes back. And then it'll swing over to the other side, reach that turning point, that the kinetic energy will go to 0 again, and it'll go back and forth. And that is the end of our discussion for today.